In this lesson, we're going to examine the properties of different types of crystals. Specifically, we're going to look at the properties of ionic compounds, molecular compounds, and of metals. Before we examine the properties, we're going to take a look at the structure of these different crystals so that we can see how the way that the structure is organized impacts the properties, and we can understand the properties more fully. Remember that when you have an ionic compound, it consists of charged species of cations and anions. So for example, if you have sodium chloride, it consists of sodium ions and chlorine ions. The bond itself is the attraction between those two ions. And when we look at an ionic compound, if we were to zoom in on an ionic crystal, what we would see is what's called a crystal lattice. And in the crystal lattice, what we see is that the ions, the positive and negative ions, are packed as tightly as they possibly can, given their size. And you'll see that they're alternating positive and negative. So in this case, the purple represents the sodium ions, and the green represents the chlorine ions. And so this is organized in what's called a crystal lattice, so you can think of like a lattice french fry or a lattice fence. And there's different lattice points. This lattice goes on in all directions. And what we'll see when we think about the properties is that it's this organization that leads to the properties of ionic crystals. For molecular crystals, what we're examining are polar and nonpolar molecules. So these are our covalent compounds, where the atoms are held together with covalent bonds where the electrons are being shared. And those bonds can either be polar or nonpolar bonds. When we think about a molecule, we want to think about it as an individual particle. So these are three examples of molecules. This is a propane molecule that's made up of carbon and hydrogen atoms. We have dimethylbutane and styrene. All of these three examples are made up of carbon and hydrogen. But so far in this unit, we've been drawing Lewis structures, and those molecules that we've been drawing with Lewis structures will eventually make molecular crystals. And if you have a sample of molecular crystals, if I have a sample of styrene, what I'm going to have is a bunch of styrene molecules that are all packed together. So we're going to use that knowledge to help us to understand some of the properties of molecular compounds or crystals. Metallic crystals is not one that we've looked at so far this unit, but it is important to add to the mix because we have studied them in previous units and we know a lot of the properties of metals. The structure of a metal is really unique. And the way that you want to imagine it is that you have the nuclei of the atoms. So if this was a sample of copper, each of these positive signs in this diagram would represent the nucleus of a copper atom. And then we have what we refer to as a sea of electrons. So the electrons in a sample of metal, specifically the valence electrons, are free to move among the sample. So it's like we have these protons or these nuclei, and then the electrons are more mobile and they're free to move within the sample. And you can kind of imagine, if you're thinking a little bit ahead, how that might affect the properties that we observe in metals. To look at the properties of compounds, we first need to discuss some of the key ideas. The first thing that we're going to discuss is the difference between intramolecular force and an intermolecular force, because it's these forces that are going to help us to think about some of the properties and explain some of the properties that we're observing. Intramolecular forces are the forces that hold the atoms together within a molecule or compound. So those are our ionic bonds, those are our metallic bonds, and our covalent bonds. Intermolecular forces are the forces that exist between molecules. And what you'll see here is some more advanced terminology that we're not going to use this year because we're going to be looking at this from a very basic level, okay? But you'll see these words in future courses, words like lattice energy and London dispersion forces. Before we go forward, we want to just make sure that we understand this difference between an intramolecular force and an intermolecular force because it's really important to consider when we're thinking about our properties. To remind yourself of what these terms mean, you can think of the intranet versus the internet. The intranet is the internet system within. So for example, at school, when you have the intranet, it's when you're accessing things that only people at your school can access. Whereas if you have the internet, that's what we'd use to communicate between schools. So intra is within, inter is between. In this example here of forming HCl or hydrogen chloride, what you can see is you have the individual atoms, and we're using a thread and needle to join the individual atoms together. This is our covalent bond, and so this is our intramolecular force. To think about where the intermolecular force is, we need to think about two unique hydrogen chloride molecules and the force that exists between the two different molecules. The analogy that we use to think about the intermolecular force is Velcro. And the reason we have the thread and the needle as our intramolecular force and then the intermolecular force as our Velcro is to help us to examine the relative strengths. Intermolecular forces are more easily broken. So I can easily separate these two HCl molecules by pulling the Velcro apart. But in order to break this bond, that's going to require a lot of energy. Okay, so those are the terms that we're going to be using. A couple of things that we can also think about initially here are the appearance of the different crystals. So when you think about an ionic crystal, they're often described as being crystalline and they tend to shatter. And this is because we want to always connect back to our structure because of the way that the ions are organized in a really ordered way. It gives really sharp edges to the surface. Okay, which is why we describe it as crystalline. And it shatters, which means it's going to break into a lot of small pieces. And that's also because of the way that it's organized. So when it shatters, it breaks. There's sort of clean breaks within the crystal when we are separating it. Okay, and in terms of metals, one of the things that we notice when we look at metals is that they tend to be shiny. Okay, and that's because of the way that the valence electrons interact with light when the light shines on the metals. The next property that we're going to consider, and we're going to compare the relative melting points of ionic compounds and polar compounds and nonpolar compounds, is the boiling and melting point of substances. When you want to think about boiling or melting, what you first need to do is think about our really basic understanding of a solid versus a liquid versus a gas. So this goes back to, basic kinetic molecular theory, where we think of solids as having the particles within the solid being close together, packed, very organized. In a liquid, those same molecules or particles are a little bit more spread out. And when you have a gas, they're even farther apart. So what we need to recognize here is that when we are going from solid to liquid to gas, we need to add energy. And the energy that we add is going to be responsible for breaking the intermolecular forces. So when you think back to our HCl example, the molecules when they're in a solid are held together with Velcro. And in order to separate them and have them spread out a little bit further, we're going to need to break some of those forces holding them together. So we're going to need to pull the Velcro and allow the molecules to separate into a liquid. And if we want to form a gas, we're going to separate them even further. Now, what's really important to note here is that when we're thinking about molecules, each one of these little circles here represents a molecule. So, for example, within this circle, I would have my HCl. And so here there's HCl, this is still HCl, this is still HCl. So when you break intermolecular forces, the molecule itself doesn't change. The bond or the intramolecular force doesn't get broken. It's just the intermolecular force that is broken. Now, if we want to compare the relative melting points of ionic compounds, polar compounds, and nonpolar compounds, what we need to do is consider the relative forces that need to be overcome. So when we have nonpolar compounds, what that means is that there is no real positive or negative within those molecules. So when we think about the intermolecular forces between nonpolar molecules, there are weak intermolecular forces. These weak intermolecular forces lead to us having lower melting points. And these are also then more likely gases at room temperature. For polar molecules, their intermolecular forces are a little bit stronger. Because when we have a polar molecule, that means that within the molecule, there's some part of the molecule that is slightly positive, and there's another part of the molecule that is slightly negative. Okay, so when you look here, if this side of the molecule is slightly positive and this side of the molecule is slightly negative, you can see you can have a force of attraction between these two molecules. So the intermolecular forces holding polar molecules together are a little bit stronger. So when we think about going from a solid to a liquid and breaking those intermolecular forces, it's going to take a bit more energy. Okay, so these are going to have kind of mid-range or slightly higher melting points, boiling points, and they will tend to be liquids, and sometimes they'll also be solids. For ionic crystals, if we consider the structure of an ionic crystal, we have our positive and negative ions that are packed together. So these are going to have a strong force of attraction, and so to melt this, we need to separate the ions, and that's going to require a lot of energy. So this is going to have a high melting point, and that's one of the things that we've observed about ionic compounds. Sodium chloride, for example, has a melting point of 801 degrees Celsius. It's very, very high relative to something like water that has a boiling point of 100 degrees Celsius. Okay. And then some of our gases, we have like very low melting and boiling points. Okay. So what's important to consider is that This is just our introduction into the differences of properties for ionic, polar, and nonpolar crystals. So we want to just keep in mind that this is just an introduction, and as we learn more about the molecules and we learn more about things like the hydrogen bonding and the London forces that I referenced before, I will be able to distinguish particles even more than what we'll be able to do at this stage. The next property that we want to consider is solubility. And for solubility, what we need to first understand is what we need to consider when we consider whether or not something's going to dissolve. So it's really important to first recognize that in order for a solute to dissolve in a solvent, there must be a good attraction to the solute so that it can essentially surround it. So if you were to zoom in and look at a solute dissolved inside of a solvent, what you would see is you would see the solute particles surrounded by solvent particles. Now you may have heard before the phrase like dissolves like, and that's a really helpful tool for helping us to remember that nonpolar solutes tend to dissolve in nonpolar solvents, and polar solvents tend to dissolve polar solutes. So for example, hydrogen chloride, HCl, is polar, and so it will tend to dissolve better in something like water, which we'll explore a little bit further in a moment. Whereas I2, which is nonpolar, tends to dissolve well in something like carbon tetrachloride, which is also nonpolar. Now, the thing about this as well to consider is that what are some of the other nonpolar solvents? So in the little activity that you did earlier, we had hexanes. That's another example of a nonpolar solvent. And we also sometimes use toluene. Okay, so these are examples of nonpolar solvents. Water is our classic polar solvent. Okay, and most of our discussion here is going to focus on water as a solvent. We're going to consider why something like an ionic compound tends to dissolve better in water than something that's nonpolar. Okay, so these diagrams will be